This problem is about the photoelectric effect, and the problem reads: light is incident on the surface of a metallic sodium whose work function is 2.3 electron volts. The maximum speed of the photoelectrons emitted by a surface is 1.2 times 10 to the 6 meters per second. What is the wavelength of the light? That is the incident light. So the work function for sodium Na would be 2.3 electron volts, and the speed of the photoelectrons coming out, the maximum speed of those for a particular frequency. Of course, this one here could be varied, but if you take a particular frequency of light being incident, then there would be a maximum velocity for the electrons. They couldn't absorb more energy than what the light is putting in minus the work function, and perhaps some more. So that one is 1.6, oops, not, that's not true, 1.2 times 10 to the 6th. Meters per second. And then what they want to figure out is the wavelength. Okay, before we even get into the photoelectric effect, I want to point something out on the wave-particle duality. I'm going to open this link here on hyperphysics. And I just go to the front page of hyperphysics. There it is. And I'm going to go to quantum physics. And then here's the photoelectric effect. That's what I'm going to click on, which is on the same page as the wave-particle duality, where it talks about here the photoelectric effect shows for light, which is usually considered a wave. And notice a moment ago I was actually talking about it as a wave. There is a wave incident on the metal, and then it turns out, oh, the way the photoelectric effect is explained is if we assume that light is a particle. And then the same turns out for particles such as electrons that we usually consider to be particles, but there are certain experiments, like the Davis-Germer experiment, that show the wave properties of such particles, and I'll talk about that later. There will be a problem about the de Broglie wavelength. Okay, I'll go a little down. There is the photoelectric effect, and again, this is all on hyperphysics, and you may read through this. And a little more. And I thought this diagram here is kind of neatly put together, that such phenomenons as, let me just right there, this is what I want. Such phenomenons as reflection can be explained in terms of waves, and here you would need Huygens principle for that, the interference of waves, and that can also be explained in particles. For reflection, that's really easy to be explained by both. Again, this is the interference of waves. This one here is kind of like the particle is like a bouncing ball, and of course it's being reflected with the same angle. Refraction is a whole lot easier explained to a certain extent with waves than it is with particles. In fact, Newton assumed, in order to make his particle theory work for refraction, that the velocity in the optically more dense medium, such as water or glass versus air or vacuum, is larger than it is in air or vacuum, and that, as we know, is not true. The other problem with having here particles is that the particle theory says that we can either have reflection of a surface, or we can have refraction of into a surface, into a medium, but not both of them together. However, the wave theory shows that you can have both due to the interference of waves that are emitted from a given point. And we can see that when we look at a window. We can see that what's going on inside on the other in the house, and we can see a reflection of the outside. Or if we look outside, we can see a reflection of the inside, and we can see what's happening outside, which means reflection and refraction are happening both at the same time on the window. And then there are these others here. These really can only be, I scrolled down too much. Interference, diffraction, and polarization can really only be explained in terms of waves, and that's the famed Young's double slit experiment from around 1800 that really made the case for that light is a wave, and the particle theory as proposed by Isaac Newton around 1680 just fell out of fashion. And then it turns out around 1900 it's back. The photoelectric effect can only be explained if in terms of particles. And that's what this problem is about. Let me see. Oh yeah, and then the interesting thing that happens, at least interesting to me, is when it is about the photoelectric effect. So here are these photons coming in the red, in the green, in the purple, and we have to think of them as being particles. And then it turns out that the way they draw them most often is actually as waves, even though here it is supposed to be a photon. Okay, let's go back to this one here and look at an applet from PhET. So I'm going to go here and, actually I wanted to start on the front page here. So go to PhET, go to simulations, click on physics, click on quantum phenomena, and then it's actually, turns out it's the very first one, the photoelectric effect. So here it is, and that's how it opens. And for example, there's incident light here at 400 nanometers, and the intensity is increased, and so the photons are shining onto the surface, and they are absorbed by the electrons that are inside the metal. The metal at this point here is sodium, which is the same as given in the problem. And so the electrons absorb the energy from the photons, and it takes them some energy in order to get actually out of the metal surface. That's what's called the work function of a particular metal, and then they go here and they go to the other side, and you can see that there's a certain current. Increasing the intensity would mean more electrons are leaving, and you perhaps saw that the current is increasing when that happens. Okay, let me get this back down to 0 here and shift the frequency to about wavelength to about 582 nanometers. Again, it's kind of weird that we're supposed to talk about photons here, but they give us wavelength and frequency and so on. Okay, here I'm going to increase the intensity, and so what we would get here is energy for each of these so-called waves coming out. So waves are coming out, and I increase the intensity, and no matter what I do, if I increase the intensity as much as I can, these electrons are not being knocked out. How can that be? Well, it turns out that they are not absorbing that wave energy, because if they did, then they would absorb enough wave energy when I increase the intensity and would eventually leave the sodium, and they don't at all. Here in this right-hand side of the spectrum, nothing happens. There's a certain wavelength that goes with the sodium where they actually do. It's about here, around in the 535. I looked it up earlier. It's about 539 nanometers, where they're actually being knocked out. And that was, yeah, people were puzzled by that. The experiment was actually first done by Heinrich Hertz in the 1880s, and then picked up by Albert Einstein in 1905. Who explained it, and that's actually what he got the Nobel Prize for, is explaining the photoelectric effect. The only way this can happen is that there is a certain wavelength frequency here, is if we don't regard the light coming in here as waves but as particles, and then each electron absorbs exactly one particle and is immediately emitted. Of course, it does take some work, the work function, in order to get out of the metal, and then the rest here is the kinetic energy. So again, it's kind of strange that we're talking about wavelength right here, but then these are actually photons coming in. Okay. Now, in the problem, it says something like the work function of 2.3 electron volts for the sodium. And I made a few measurements here. 400 nanometers is coming out right now. I just put the intensity to 100%, so I'm in the purple here, and then there's something called a stopping potential that I can oppose now these electrons and try to slow them down until the current right here goes down to 0. And I did that prior, and I come up with roughly 0.80 volts is opposing that. If I go to a lower wavelength, for example 304 nanometers, again now they're of course faster because they have a higher frequency, respectively a higher photon energy, and therefore the electrons, you have a higher kinetic energy overcoming that stopping potential. And then if I increase here stopping potential at some point, again I'm going to come up with a 0 current, and I measured that earlier as 1.78 here, 1.77 volts. Still some current is coming through, but if I go to 1.78, no electrons are hitting the other electrode. And then I took a couple more measurements, and basically this is what I got. This is the numbers I just showed you: 400 nanometers, 304 nanometers, and I measured a stopping potential of 0.8 volts, 1.78 volts, and then I took a couple more at 202 nanometers, 127 nanometers, and you can play with that and with the applet and come up with the same numbers. And then I calculated this one here, which is the energy of the photons in electron volts. And notice this 1240 here. I did it as follows. Just going to type that in here. The photon energy is given as the Planck's constant times the frequency, respectively. In this applet here, the wavelengths are given, so I'm going to write it instead as Planck's constant times the frequency, times the speed of light divided by the wavelength, so divided by lambda. And now I would have it in units of joules. And if I wanted to have that now in units of electron volts, because the electron volt then corresponds to the voltage that I'm able to measure with the voltmeter, with the stopping potential, then what I would do is I would take the same as H times C over lambda, and also divided by the electron charge E, and then I have it in electron volts. And that Hc here, right here, Hc divided by that E back here, that's the 1240 that you saw right there, which appears here always, and then I divided by the wavelength from over here. And I graphed these here, and I only did 4. Notice that the slope of this graph here is virtually 1, which makes sense because both this one here is energy and this one here is energy. And then the y-intercept, which is a negative here, that's it here, that's the y-intercept, 2.3 electron volts, and that's what you see given in the problem. So basically what I did here with that is I confirmed that the work function for sodium is actually 2.3 electron volts. All right. All right. So therefore I'm going to have lambda equals Planck's constant times the speed of light divided by the maximum kinetic energy, and the work function, always, this happens always here when I try to write something that is too small, then it doesn't like it. Okay, there we go. And of course the kinetic energy is 1/2 times the mass times velocity squared, and here of course it's the mass of the electron. There you go. Okay, and then it's just a matter of plugging in numbers. This one here is 6.626 times 10 to the negative 34, and speed of light is 3.0 times 10 to the 8th. Then 1/2 times 9.1 times 10 to the negative 31 kilograms. Velocity is given in the problem as 1.2 times 10 to the 6 meters per second. And then the work function here, well, it's 2.3 electron volts, but notice that everything else here will come out in joules, joules, so this one has to be in joules as well. And so therefore multiply 2.3 electron volts by 1.602 times 10 to the negative 19 joules per electron volt. That's the conversion between the two. And then everything is going to come out in joules. Oh, I take that back. This is joules, this is joules. I take that back. That one here is joules times meters, and therefore this one here will come out in meters. So lambda equals something in meters. I can actually make a quick calculation here so you get an idea on how much it should be. I'm going to calculate the kinetic energy of the electrons. So 1/2 times the mass of the electron times the given speed in the problem squared, and then I divide that by the charge of the electron in order to get this one here in electron volts. And that's just to compare, because in the problem, I'm sorry, not in the problem, but in the applet earlier I was measuring in volts, and it turned out that it's easier to look at electron volts as far as the experiment itself is concerned. And so I have 4.08 electron volts for the electrons. So when I look at here the stopping potential, I'm somewhere around here, 4.08. Notice a little bit more than that, which means a little bit less than 202 nanometers. So 202 nanometers is 2 times 10 to the negative 7 meters. So that's what you have to expect around there, 2.0 10 to the negative 7 meters, a little bit less than that, because that stopping potential here is a little bit higher, or the maximum kinetic energy.